Okay, so we're going to look a little bit at Newton's third law of motion, sometimes called the law of reaction. And we're going to talk about how it's related to momentum, so a little something new, but we'll go back and talk a little bit of what you would have learned in your first physics course as an undergrad, where you're talking about, every action has an equal and opposite reaction, which I just have a little something here just so you can kind of see the law in words. Just right here, for every action force, there's an equal reaction force. In other words, if you push a brick wall, the wall pushes back with an equal force. I just also got this little picture that I thought was kind of cool. It's this kid pulling this rope that's connected to the wall, and it's almost like there's an elephant he's pushing it against compared to this brick wall. Obviously, the elephant's probably stronger, but you're feeling the same force it would give you. So let's talk a little bit slowly here, and we'll talk about maybe what you would have learned in your Physics 1 course. Great, I have to draw. So let's draw. The reason why this seems somewhat intuitive. If you were to push against a wall, you could convince yourself there is a force pushing back on you. The reason why it's not intuitive is examples like the one I'm going to give you, and we'll talk about it. Say you have a guy. We'll put his hands over here. And we'll say he's holding a baseball bat. I know it's not a good one. And then there's a ball, it's a very big ball, coming at him at some speed. Well, at some point, what we're going to see it's probably not how the ball or the baseball bat looks. It's going to come in contact with the ball. And at that point, there's a force. There's a force of the bat exerted onto the ball, and there's also a force of the ball exerted on the bat. And if you were to watch this, obviously, we would know what would happen is the ball goes flying way out over here. It's flying at some velocity over there. It's kind of hard to imagine that the force that this ball is feeling that's throwing it that far off is equivalent to the exact same force that the bat felt over here. Now, the reason why that seems a bit weird, let's remember force is equal to mass times acceleration. Let's just look at that example. And acceleration can, if we divide by mass, is force divided by mass. So even though they have the same forces, what we're seeing is unequal acceleration. And that's fine. Nothing about Newton's law says they have to have the same acceleration. It just says that they have equal and opposite forces, which is what we're seeing. The part that trips people off and they confuse it for force is they're seeing a radical change in acceleration. The bat doesn't really experience much of an acceleration. The ball is moving this way. The moment of impact, it's still technically moving that way, and then it just goes all off in the other direction. Well, you have to remember the mass of a little baseball is much, much, much less than the mass of a baseball bat. So that's why we're seeing this drastic change in motion. It's not because the forces are different. It's because the masses are different, and you're seeing this massive change because of the mass. So hopefully that makes sense. The bigger the mass, obviously, the smaller the acceleration you're going to get. So hopefully that makes sense. Now let me draw just a little picture. Let's say we have object 2. Let's say we have object 1. And let's say that this is the force. This is the force. This is the force 2 on 1. And the reaction force, that's too big. It looks a little too big. It's a little bigger. It's opposite. It's negative F2 on 1. And these are vectors, so I should draw the little arrows. So what this is saying is F, the force of 1 exerted onto 2, is equal to negative F2 onto 1. Okay? So when you're switching these numbers, the way I like to think of it, if you don't recall, is this is the force exerted by something onto something else. The force of something onto something. Okay? So if it's 1, then it's object 1. It's the force exerted by object 1 onto object 2. It's the force of object 2 exerted onto object 1. Okay? So the big thing with Newton's third law of motion, that's one way to abbreviate it, is this. One way to think of it, and a helpful way to think of it, is if object 1 exerts a force, which we'll call F2 onto 1, on object 2, object 2 exerts a reaction force F1 onto 2. They're third law partners. Okay? This and this, because of this is supposed to be a comma. Because the numbers are flipped, we can call those third law partners. Okay? And just as we said before, the force of 1 onto 2 is equal to negative F2 onto 1. Now, the important thing here, so this should all, for the most part, be kind of just review of Physics 1, which is good. It's good to review that. Classical mechanics is, it's the same course. You'll just it'll just get more difficult. But one way you probably maybe haven't seen it is how this is entirely related to momentum, which is what we're going to talk about here. Okay, so I'm going to draw a picture, which I'm sure everyone's excited for my picture drawing abilities. What color should I use? We'll do blue for reasons you'll see soon. And then we'll do this. This isn't the color, but we'll do orange. So let's say we have object 2, which we'll call the Earth, and object 1, which we'll call the Moon. So this is the Moon. And we'll say this is the Earth. Okay, now there's a force. We'll make it a little smaller just to help us here with room. There's a force from here to here of 2 onto 1. And likewise, there's a force 1 onto 2. Okay? So we can think of this as being, gravitational pulls. The force of 1 exerted by 2. The force exerted by 1 onto 2, or however you want to think about it. The important thing is we see that the moon is going to be pushed towards the Earth, right? And the Earth is going to be pushed towards the moon. Okay? So the force onto exerted by the moon. The force exerted by the moon, or the force on the moon exerted by Earth. Okay? So let's also add some external forces. Let's say we have the sun. And the sun also pulls that, right? So we can say this is F2 external. This isn't part of our system per se, but maybe it's an alternative force. And this is force 1, external. I think I have enough room. Okay. Now let's work through this really quick. The sum of all forces for 1, I will call just F1. And what's that equal to? Well, that's going to be just the force exerted by the Earth onto the moon, okay, plus F1 external, whatever the external forces may be. And in fact, you could think of external forces as not just being the sun. Maybe it's the other planets, and it's the vector sum of all the other forces acting on the moon, or whatever one was. Likewise, if we look at F2, we're going to call that the sum of all the forces, just F2. That's going to be 2 onto 1 plus F2 external. Same logic, right? Okay. But let's remember, force is equal to our change in momentum, the time derivative of momentum. We talked about that in Newton's second law. That means the change in momentum of 1 is equal to force 1, which is equal to F1 2 plus F1 external. Okay, that's supposed to just be equals. And we can use the same logic for the momentum on particle 2 or planet 2 or moon, whatever you're calling 2, it doesn't really matter. That's equal to just F1 2 plus F2 external. Okay, so the change in momentum is our force. So I'm just taking this and putting it basically here and here. Hopefully that makes sense. Okay. Now the momentum of our system, or I guess I would say, well, we'll just do momentum, not the change yet. The momentum of our system is equal to momentum of our first particle plus the momentum of our second particle, or Earth and Moon, doesn't really matter. You can call it I think they normally call it particle, but you could think of it as planets, you could think of it as whatever. So, the momentum, the change in momentum of our system is equal to the change in momentum of our first particle plus the change in momentum in our second particle. And what is the momentum of our system? Well, we're just this and this. We can get from here and here. So let's write that out. The momentum of our system is F2 onto 1 plus F1 comma 2 plus F1 external plus F2 external. But we know from Newton's third law that these are third law partners. They're equal and opposite. So these can kind of just go away, right? So the change in momentum, that's a vector. Cool, I've been keeping my arrows for the most part. Of our system is just force 1 external plus force 2 external. And we'll just call that our total external forces on our system. Maybe we'll call that of the system. Okay? So what does that mean? Well, if, I'll do this in a different color because it's kind of the big idea. If F external of our system equals 0, then our momentum is constant, right? Because if this were the case, then the change in momentum of our system is equal to 0. Well, what that means is there's no change. If there's no change, then our momentum is constant. And what we saw here, and what we just showed, is conservation of momentum, which I'm sure you used a lot in Physics 1. And this is another way of kind of looking at it and seeing where it comes from. And hopefully it makes sense now that we talked about Newton's second law being a differential equation and we can think of it as different in different ways. It makes sense why in Physics 1 you would identify, when you're doing a momentum problem, you would identify your system and you would see, okay, we're looking for external forces. Are there any external forces? If there's not, momentum's conserved, right? So that's why we did all that, and hopefully that makes a little bit of sense.